Hi guys, Rod from Bensame Thought Videos here, and this is the fifth video in my series examining the underlying philosophy that gives rise to the scientific method. So last week we began examining the tool of mathematics. I suggested mathematics is like a transport machine that can take you from one bit of scientific knowledge to another. We also looked at how mathematics is born from enumerating categories, and we began to develop the basic number system. We also used a skiing analogy in terms of grading our mathematical concepts. Last week's concepts were definitely in the gentle mathematical footholds of basic arithmetic, which, if you are a skier, would be a green run category. In this video, we are going to begin by introducing algebra, and then continue to develop our mathematical number system. So last week we looked at the four basic operations of addition, subtraction, multiplication and division. We also spent some time considering the meaning of zero and negative numbers and show how it can take some work to put a correct interpretation on a pure mathematical concept. We also introduced order of operation in terms of calculation, and finally we began to think about the beginnings of geometry with lines and angles. If you haven't watched that video, it might be worth pausing this one and going to the description below where I've placed a link to it, so you do not miss out on anything I have spoken about so far. Okay, so the first thing we shall do this week is introduce algebra. Algebra starts with the idea of trying to find the value of an unknown inside an equation. The most basic algebraic equation might be something like x plus 4 equals 7. Most of us can quite quickly, in our heads, calculate that x must be 3 for this equation to work. Quite simply, algebra is just introducing letters to stand for numbers that are to be determined. It is also pretty simple to develop rules for solving algebraic equations. For example, in the equation we just solved in our heads, if we formalize what we have done, we can see that to get back to x, we must subtract 4 from the left-hand side of the equation. This means in order to keep everything equal, or balanced, we therefore must subtract 4 from the right side of the equation as well. When we do this, we get 7 minus 4, which equals 3, and so therefore x equals 3. All very simple. We can now quickly move to equations that contain brackets. We talked about using brackets when we wanted to change the natural order of mathematical operation. We considered the equation 4 plus 6 times 10. And using the rules of operand precedence, the correct answer to this sum is 64. If we want to specify that we should apply the addition before the multiplication, then we need to use brackets. So it becomes open brackets 4 plus 6 close brackets times 10 is equal to 100. However, we can still multiply before adding if we multiply the 6 by 10 first and the 4 by 10 second. We can then add the resultant two new numbers of 60 plus 40 to get 100. We can quickly see why this works with our original diagram of oranges that was used to introduce multiplication. In the diagram, we have 4 sets of 6 oranges, which is 24. However, we can partition each set of 6 oranges into 2 sets of 3. We still have 4 sets, it is just that we now have 4 sets of 3 oranges plus 4 sets of 3 oranges, so we can see quickly how this rule works. Thus, if we have the algebraic expression 4, open brackets, a plus b, close brackets, then this can be expanded to equal 4a plus 4b. Since, of course, we can't add the expression first because we don't know the values of a and b. Our expansions can even get a little more complicated. Take, for instance, the expression open brackets a plus b, close brackets, times open brackets c plus d, close brackets. Well, in order to do this, let's first let a plus b equal r. We then get r, open brackets c plus d, close brackets. And we know that this equals RC plus RD. Now we just need to put back a plus b for r, and we get open brackets a plus b, close brackets c, plus open brackets a plus b, close brackets d. And expanding those two expressions, we get AC plus BC plus AD plus BD. We can also show the same thing geometrically. We spoke about angles last time, but with lines we can also create shapes. If we think of a rectangle of sides A and B, we can multiply the two sides together to calculate what is called the area. However, this is exactly the same as multiplying our groups of oranges. It is just that now, rather than having a set of oranges, the numbers are associated with a side length. Therefore, the same rules apply. The area of a rectangle is just its two sides multiplied together. So the area of the rectangle with sides A and B has an area of AB squared. We shall return to the square bit in a moment. Now I'm showing a rectangle which is made up of two sides, one A plus B and the other C plus D. We can see that when we multiply these two sides together, we create four different shapes shown in different colours. The four shapes have the areas AC, BC, AD and BD. So the total area of the large rectangle must be AC plus BC plus AD plus BD. The same answer we got using our algebraic method. Of course, this must be the case for our mathematical system to remain logically coherent and so meet our zeroth axiom. Okay, so we can now see algebraically that if I add four A's together, I get 4A. What about if I want to indicate the other operation of multiplying four A's together? How am I going to express this algebraically? Well, we need to create some new syntax, and here we introduce a number that is to the right and is superscripted above our variable. So A times A times A can be written as A with a superscripted 3 next to it. We say this is the cube of A, or A raised to the power of 3. Now here's where it is going to get interesting. We now have a meaning for A raised to n, where n is a positive integer. For example, A raised to the power 5 is just A times A times A times A times A. However, once we stick a superscripted number next to our algebraic symbol, we need to generalize it for every possible number, and that includes negative numbers, 0 and fractions. This is interesting because last week I spoke about how when first enumerating things, we can develop the concept of a negative number as the inverse of a positive number, and in so doing, we need to think about how this lines up with the real world. In the same way, we now need to think about what raising a number to a negative number means. In other words, we need to give this negative power or indice meaning, which keeps our mathematical system logical and consistent. Again, the zeroth law of coherency. Okay, so let's do that. We said last week that a negative number decreases a positive number, so it must also do this with our indices. Thus, if I have 4 raised to the power 2, and I then multiply by 4 raised to the power 2, we have already established that this must be 4 to the power 4. Therefore, if I have 4 to the power 4, and I multiply it by 4 to the power minus 2, then it must decrease my original indice by 2. In other words, 4 minus 2 is 2. If now I put this into fractional notation, we can see that therefore 4 to the power minus 2 must be the same as 1 over 4 squared, since this is the number that will decrease the indice of my original expression, 4 raised to 4 to the power 4 squared, as now shown on the screen. So by recognizing that a negative number is the inverse function of addition, and by defining positive indices as enumerating how many times the number is multiplied by itself, we have established that a negative indice must therefore be 1 over the base number raised to the value of the negative indice as shown on the screen. From here, we can now quickly define the meaning of a number raised to 0. If we take the number n and raise it to a positive and negative power, as I have done on the screen, we can write out the meaning of these indices underneath. Now what we do is just multiply all our negative indices by n over n, which is multiplying by 1, so not changing the value of all the negative indices. And we see that all our negative indices now have n in their numerators, just as with the positive indices. We now see that n raised to a negative 1 is the same as 1 over n, or n over n squared. Likewise, n raised to 1 is just n. N raised to 2 is n squared, while n raised to negative 2 is 1 over n squared, or n over n cubed. Lining up our indices, if n to the minus 1 equals n over n squared, then n to 0 must equal n over n, which is just, of course, 1. Therefore, n raised to 0 is always 1, no matter what the value of n. Although for some of you this might seem really obvious, it is really neat, in my opinion, how all these rules come to life as we create an initial mathematical syntax and then explore using that syntax exactly what the numbers will mean if the syntax is consistent with our initial starting definitions of the 4 mathematical operands. Yet we are not quite finished defining the meaning of our indices because we have not dealt with indice fractions. For example, what is n raised to a half power? Well, firstly, we need to come up with the situation where we are multiplying rather than adding indices. We have already defined indices as such that when we have n to the x times and n to the y times, the answer, if we multiply these together by definition, is n to the x plus y. So it follows that in order to multiply indices, we must take our original number raised to a certain power and then raise the number again. Now we need a way to write this, so we once again make use of our brackets. Thus, n to the x raised to the y is now shown on the screen. Note the use of brackets to separate what is known as a double exponentiation, and it is equal to x times y. Once we have this, the meaning of the fractional power becomes obvious, because we know that 2 times a half is 1. Therefore, raising a number to a half power is the same as finding a new number that when squared gives us back the number we are raising to the half power. In other words, raising something to a half power is the inverse function of squaring a number. Likewise, this must apply to all of the fractions. So if we raise a number by 10, meaning taking a number and multiplying it by itself 10 times, then if we start with that new number that we've just obtained and raise it to 1 over 10, then effectively the number we get back is the original number before multiplying it by itself 10 times. And with that, we have just completed describing the syntax of indices and how they are used to code the multiplication of base numbers by themselves multiple times. Now let's continue to expand our development of algebra. We can obviously create an equation which has more than one variable in it, and once we do this, we create what is known as a mathematical function. On the screen, I have created the simple mathematical function y equals x squared. Now, as x takes a given value, so y takes on a corresponding value based on the mathematical relationship between the two variables. So we see that when x equals 1, y equals 1. When x equals 2, y equals 4. When x equals 3, y equals 9, and so on. When x equals minus 1, y equals 1. When x equals minus 2, y equals 4, because remember, minus 2 times minus 2 is 4. A negative times a negative is a positive. As discussed last week, we can visualize the output of this function by utilizing 2 of our 3 spatial dimensions to create a graph, as I have done here. This distinctive shape is called a parabola. Finally, we can manipulate this function as shown. If we raise both sides by a half power, we get y to the half equals x. If we swap the variables around and graph this function, we get the inverse function of y equals x squared, which is y equals x to the half, which is now shown on the screen. Yet of course we can go further. We can create functions with any number of independent variables. The variables on the right side of the equation are called independent variables because we set the values whereas a dependent variable on the left side is controlled or depends on the other variables in the mathematical function. Obviously, if we try to graph these, we quickly run out of independent spatial dimensions to plot these higher order functions. But if we have a system of equations with, say, 5 unknowns and 5 equations, then in theory it might be possible to determine a value for each of these 5 variables. The 5-dimensional point, which is a solution to all 5 equations, is where the 5 functions intersect in a 5-dimensional hyperspace. These concepts will not be explored further, however, because they are not needed on our narrow mathematical path to developing E equals mc squared. We shall finish this video by now applying our new mathematical tools to some basic physics, and that is the phenomenon of motion. So again, in the reality in which we find ourselves, we exist in a particular space-time location, and every so often we want to move to another place. In order to do that, we must move, and in order to do that, we must change our state from rest to some sort of motion as we head to our destination. We also are aware that a certain amount of time passes as we move from point A in space to point B in space. We also know that the faster our speed, the less time it takes to get from point A to B. With these simple rules, we can create some simple equations to capture these observations mathematically. We can define our speed as simply the distance travelled over the time taken. This means that the shorter time it takes to travel a certain distance, the higher the numerical value of our speed, and this is exactly what we need to match our experimental observations. Now, strictly speaking, while we have spoken about distance travelled, we measure that distance by comparing our starting location to our final location. Therefore, distance is actually a measure of the change in location, while the time taken is also calculated by calculating the difference between 2 points of time. And so the time elapsed can also be thought of as a change in time. Thus, more formally, we can write speed, or if we want to code the direction of travel, we can use the term velocity, which in physics is called a vector. Velocity, therefore, will equal the change in spatial position divided by a change in time. Incidentally, if we are dealing with direction, we might define, say, moving to the right of our computer screen in this video as a positive direction, in which case that means that moving the opposite way must be a negative direction, because it is cancelling out moving in a positive direction, and so must therefore be assigned a negative number. Again, an inverse function. Once again, we now see our negative number is taking on a meaning, this time in terms of the direction of travel. Yet there is something else we need to code from our experience of travelling from one place to another. We know that in order to start our journey, we must accelerate from rest to a certain speed, and then maintain that speed until we reach our destination. And then, as we reach our destination, we must decelerate so we become stationary again at where we want to be. This means that our speed, like our position in space, also changes. We also know that the quicker it changes, the faster the acceleration, and so we can define acceleration as a change in speed over a change in time, just as we define speed or velocity as a change in space over a change in time. Once we have defined acceleration, it is then possible to do a physical experiment to see what influences acceleration. When we do that, we soon become aware that whatever we use to get an object moving in the first place, that thing, which physicists name a force, will result in less acceleration the heavier the object is. In other words, if we have a pool table or a billiard table and we strike a pool or billiard ball with a cue using a certain stroke of the cue stick, and we do the exact same action but the ball is twice as heavy, then the second ball's change in motion is only half as great, meaning its final speed is only half the speed of the ball that is half its weight. The stroke we applied is a force that is created from our muscles contracting to move the cue so that it strikes the balls, while the weight of the ball is directly related to what is known as the ball's mass. From experiment, it can be shown that force equals mass times acceleration when friction is not present. This is just a physical law that is observed to be true from the data coming from our universe. In other words, the maths is providing the coherency part of our science, while the data is used to line up our theory with actual experiment, hence meeting our axiomatic tests of truth, that our model is both coherent and correspondent with reality. We now need to look a little more closely at exactly what is happening when we strike our cue ball. If we look at everything in slow motion, we see that our Q-tip is in contact with our cue ball for a finite amount of time, as it literally pushes the ball along from its resting position. As it does that, the ball accelerates, but quickly the ball moves away from the Q-tip, and at that point, where there is no more contact between the cue and the cue ball, the positive force on the ball and the acceleration also must return to zero, since Newton's first law states that an object will remain at rest or in constant motion unless acted on by an external force, ignoring friction, of course. Again, Newton's first law simply comes about because we are aligning our theory with what is actually being observed to happen in our universe. So to calculate the final velocity of our cue ball, we simply multiply the average acceleration of the cue ball during the time the Q-tip was in contact with our ball by the time period. Now, returning to our force equals mass times acceleration, if we multiply both sides of this equation by the time that the force acted on our ball, we get mass times acceleration times time on the right side and force times time on the left side, which, if we just have a constant acceleration, will equal mass times final velocity. This is because our initial velocity of the cue ball was zero, and acceleration is equal to a change in velocity over time. The change of velocity is just equal to the object's final velocity minus zero, divided by a time period the force was acting on our ball. So when we now multiply the acceleration by the time the force was acting on the ball, the time variable disappears and we are just left with mass times velocity. Mass times velocity is defined as the object's momentum, and it turns out that the momentum of a system is a conserved quantity. Now, just as we can determine velocity and momentum by considering how long a given force acted on the object, we can also consider the distance travelled by the object during which the force was acting. We can see this in our pool cue example, as the cue not only is in contact with our white cue ball for a given amount of time, but it is also pushing our ball through a certain distance as the cue slides through our fingers. If we therefore now multiply our force by that distance, we must also multiply the other side of our force equals mass times acceleration formula by distance, leading to this side now equaling mass times acceleration times distance, or MAD for short. Now, the distance the ball travels during which the cue is accelerating it is going to be equal to the average velocity of the cue ball multiplied by the time the cue was in contact with the cue ball. We know that the cue ball started at rest, so its initial velocity at time zero was zero. By the end of the acceleration, it had reached its final velocity, which we call v. So the average velocity during the acceleration time period is just v plus 0 over 2, since this is how we obtain an average. Now, v plus 0 over 2 is simply the same as a half v. So we now know that the distance travelled during which the force acted is a half vt. And if we now put this into our F equals ma formula, we get force times distance equals mass times acceleration times a half vt. But acceleration equals the change in velocity over time. Now, the initial velocity is 0, so as we just showed above, this means acceleration is just equal to the final velocity divided by time. So we now have force times distance equals mass times velocity over time times a half velocity times time, which simplifies to force times distance equals a half mv squared. Like momentum, this quantity is also conserved and is called kinetic energy. Kinetic energy is just a subtype of a much more general physical quantity called energy, which is the left side variable of Einstein's famous E equals mc squared equation that we are working towards proving. The reasons why physicists like to calculate energy is because forces like gravity exist as a force field. A force field is not some weird space fiction concept, but simply the idea of a force that acts through a spatial dimension. If we think about our experience living on planet Earth, we are subject to the force of gravity that exists in our spatial vertical dimension. This force is directly proportional to your mass, and it acts constantly along the vertical dimension. Now, when you are standing on Earth, the Earth itself pushes against gravity, so you remain at rest but feel the force as your weight. However, if you climb a tree and jump out, you accelerate towards Earth for as long as you move through the distance from the tree to the ground. Hopefully, this distance is short enough that you don't break a leg. Sadly, however, if you were to jump off a cliff, the distance and time over which the force of gravity acts to accelerate you is great enough to give you a velocity which, when you hit the Earth, imparts an opposite force in a much shorter period of time to decelerate you so rapidly that you break apart. Thus, the time a force acts is directly related to its distance and vice versa through the object's velocity, and thus we can either calculate force times time, which is called impulse, to get momentum, as Sir Isaac Newton did, or force times distance to get kinetic energy, as his famous rival Leibniz did, with both quantities being conserved. As an aside, both geniuses lived at the same time, and both are credited with simultaneously discovering calculus, which we shall start to learn about next week. Also, in the next video, we shall prove Pythagoras' theorem, and we shall make use of both Pythagoras' theorem and calculus to show where the famous E equals mc squared formula comes from. Okay, so that is my thought video for this week. If you like this video, please do hit the like key, and if you want to see more of my content, then please do subscribe to my channel by hitting the subscribe button and the bell notification key below. Until next time, I hope your body and mind are in a good place, and bye for now.